First, let's look at linear transformations that are one-to-one. So just to be precise about what exactly one-to-one means, a linear transformation, or indeed any function, is called one-to-one if every input produces a different output. So another way to say that is if you have different inputs, they produce different outputs. Another way to say that is if you have two outputs that are the same, they had to have come from the same input. So if t of v equals t of w, then v equals w. Another name for being one-to-one is injective. I guess some people like to have a word that sounds a little fancier than one-to-one, maybe. Now, it turns out that one-to-one transformations have a really nice property when it comes to linearly independent vectors. So suppose we have some linear transformation that goes from a subspace V to a subspace W, and suppose we have some collection of linearly independent vectors in V. Then it turns out that if you apply the transformation to these linearly independent vectors, what you get is linearly independent vectors sitting in your codomain. So right, these t of v1 through t of vk, these are all in W. So let's see why this is true. So we're going to suppose that we have these v's in capital V that are linearly independent. And let's also suppose that we have some linear dependence relationship, among the among t of v1 through t of vk. So suppose a1 times t of v1 plus a sub k times t of vk. Suppose these add up to 0. Okay. Well, we can use the linear transformation properties for t to write this as t of a1 v1 plus dot 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 up through a k vk equals 0. And this is the vector 0, right? But there's another vector that gets sent to 0. It's the 0 vector, right? Any linear transformation sends the 0 vector to 0. So here we have two vectors that get sent to the same thing. This one, the linear combination, and this one, 0. But if our linear transformation is one-to-one, that means that these two vectors with the same output have to actually be the same vector. So a1 v1 plus dot 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 up to ak vk has to actually be equal to the 0 vector. But remember, the v's are linearly independent. So that means that a1 has to be equal to 0, and a2 has to be equal to 0, all the way down to ak has to be equal to 0, right? We have this linear dependence relationship among the v's, but that means that actually all the coefficients have to be 0. That's what it means to be linearly independent. So now let's take stock of what we showed. We started with these vectors, right? We assumed we had a linear combination equal to 0. We showed that all the coefficients had to be 0. But that means exactly that these t of vi's, these are all linearly independent. So t of v1 up through t of vk are linearly independent. And that's what we wanted to show, right? So this is not true for most linear transformations. This really is a special property of one-to-one linear transformations. It sends linearly independent sets to linearly independent sets. You can see we used the one-to-oneness of t in a crucial way in this step right here. All right, so just to make sure we understand the definition of being one-to-one, let's look at an example. So let's decide, is this linear transformation one-to-one? Well, if you look at this linear transformation, I mean, like all linear transformations, it's really just multiplication on the left by some appropriate matrix. Which matrix is it? Well, it's 2 minus 4 minus 1, 1, 5, 8. Okay. So how can we check if a linear transformation is one-to-one? Well, what we can do is assume that two inputs produce the same outputs, right? So we can put two different vectors in here, assume that they produce the same output, and then eventually show that the inputs had to actually have been the same. So let's call this input maybe xy, and this input maybe AB. Okay, so what we want to show, or what we hope to show, if this really is one-to-one, is that xy equals AB. Okay, well, t applied to xy, that's just this matrix, 2, -4, -1, 1, 5, 8, times xy. And then t applied to AB, that's just the exact same matrix, -2, -4. Sorry, this shouldn't be -2, this should be a +2 here and here. -1, 1, 5, 8 times AB. Okay, so let's see. This is a linear equation, right? This is really a system of two linear equations, because this matrix product on the left, once you do the matrix product, it will produce a vector with 3 entries. Same thing on the right. So this equation of matrices or vectors is really 3 different linear scalar equations. And to solve this sort of thing, we would just row reduce. But remember, row reducing really amounts to multiplying on the left by elementary matrices. And we can do that on both sides of this equation. And because this matrix here is the same on both sides of the equation, when we multiply on the left by an elementary matrix on the left-hand side, we do the same on the right-hand side. And so we'll actually end up doing the same row operations on both copies of this matrix. So as we row reduce this matrix, we're actually row reducing both of these matrices. And furthermore, as we do this row reduction, all these multiplying by elementary matrices never change the vector of variables over here, because we're multiplying on the left by these elementary matrices. So what this all comes down to is we can row reduce this matrix and know ahead of time that the row reduction on the right will be working exactly in the same way. So let's go ahead and row reduce this matrix. I guess maybe the first thing I'll do is interchange row 1 and row 2. So that's going to give me -1, 1, 2, -4, 5, 8. Then let's do row 2 plus 2 row 1 and row 3 plus 5 row 1. Okay, this is going to give me -1, 1, 0, -2, and 0, 13. Do I have that right? I'm adding 5 times this. Yes. Okay. But now we can, let's see, let's multiply row 1 by -1, and let's multiply row 2 by -1/2. So this gives me 1, -1, 0, 1, 0, 13. And then we can use this one here to zero out the stuff above and below. So we're going to get 1, 0, 0, 1, 0, 0. Okay. So what this means is this system of equations, when we finish row reducing it, we get 1, 0, 0, 1, 0, 0 times xy equals 1, 0, 0, 1, 0, 0 times AB. But when we do this matrix multiplication, what we get is xy0 equals AB0. And this tells us that, yes, indeed, x is equal to a, y is equal to b. So our beginning vectors, x, y, and ab, had to have been the same. So this linear transformation T is 1-to-1. Okay. But let's sort of take a step back and think about the bigger picture. In this, how would this calculation work out in general? So if we have some linear transformation represented by a matrix, asking if it's 1-to-1 is going to be solving exactly this kind of system where you have the same matrix on both sides and vectors full of variables. And when you row reduce, right, what happened here is these vectors had to be the same because, essentially because there's a pivot in every column here. Right? Because there was a pivot in every column, when we did this matrix multiplication, x and y showed up and a and b showed up, and that's what forced them to be the same. So what we're seeing here is that a matrix A represents a 1-to-1 transformation exactly when the reduced row echelon form of A has a pivot in every column. Okay, so I guess really we just showed this way, but you can see that the argument works backwards as well, so this implication also is true. Checking if a linear transformation is 1-to-1, the defining property of being 1-to-1 is a little bit clumsy to work with, but knowing that we can instead think about the reduced row echelon form of the matrix A means that there are a number of conditions that are equivalent to being 1-to-1, but much easier to check. So let's look at a few of those. So it turns out, if you have a linear transformation from Rn to Rm, or really from any subspace of either of these, and the matrix for this transformation is A, then the following statements are all equivalent. So let's prove that these are all equivalent. So let's suppose T is 1-to-1. Let's show that the rank of A has to be n. Well, remember, 1-to-1 is equivalent to having a pivot in every column. But if you have a pivot in every column, that's the same as saying that the number of pivots is the number of columns, which is n in this case. But if you have n pivots, that means the rank is n, right? So this is if and only if rank A equals n. And all of these are if and only if statements, right? So that means that these two are equivalent. Okay, well now let's show that rank A equals n is equivalent to the nullity of A being 0. Well, this is just a direct consequence of the rank nullity theorem. So the rank nullity theorem says that the rank of A plus the nullity of A is equal to n. But if the rank of A is n, then the nullity has to be 0. And if the nullity is 0, then the rank has to be n because of this equation. So these two are equivalent. Okay, well now let's look at number 4. So let's show that the nullity of A being 0 means that if T of V is 0, then V is 0. Well, this implication is actually, I guess it's the reverse implication that's the most obvious one. So this implication, is clear because if T of V is 0 implies V equals 0, that means that the null space of A is just the 0 vector, right? This statement is essentially saying the only vector that gets sent to 0 is 0, so the null space is 0. But if the null space is 0, the dimension of the null space is 0, but the dimension of the null space is what we called the nullity. But actually, all of these statements run backwards. If the nullity is 0, that means the dimension of the null space of A is 0, because that is the nullity. But if the dimension is 0, the only dimension 0 subspace is the subspace that contains only the 0 vector. So that means the null space is 0. But if the null space of A is 0, that means the only vector that gets sent to 0 by multiplication by A is the 0 vector. Right? So if we multiplication by A turns it into 0, then that means V is equal to 0. But this is equivalent to the statement that if T of V is 0, then V is 0. So this implication goes both ways. All right. Now the tricky condition here is number 5. Okay, so let's think about this one. So T has a left inverse. Well, what is a left inverse? We know that an inverse function would satisfy this. So T inverse composed with T is the identity, and I guess this would be the identity on Rn. Okay. This notation, by the way, the identity function on Rn is the function from Rn to Rn defined by the identity function of a vector is just exactly the same vector. So the identity function is just a function that gives back to you whatever you gave it. So a full genuine inverse satisfies this equation and also this equation. T composed with T inverse is the identity on Rn. Right? So a left inverse is something that only satisfies the first one. Right? So a left inverse is a transformation S so that S composed with T is the identity on Rn. Okay, so now let's show that having a left inverse is equivalent to being 1-to-1. So let's assume that we have assume T is 1-to-1. So 1-to-1, often abbreviated 1-1. So assume T is 1-to-1. We need to come up with this linear transformation S. Okay, so let's let V1 through Vn be a basis for Rn. Okay, we could use the standard basis, but really any basis will do. Let's let W1 be T of V1 and W2 be T of V2 and so on up to Wn be T of Vn. Okay, now because T is 1-to-1, right, these W's have to be linearly independent. Something that we showed about 1-to-1 transformations is they send linearly independent vectors to linearly independent vectors. But these V's are a basis, so the V's are linearly independent. So the V's are linearly independent, T is 1-to-1, and so the images of all the V's have to be linearly independent. So these W's are also linearly independent. All right, so now we have n vectors, the W's, linearly independent in Rn. But that means that m has to be greater than or equal to n, right? You can't have more linearly independent vectors than you do dimensions in your space. So n has to be less than or equal to m. So we can extend this linearly independent set, W1 through Wn, to a basis, W1 through Wm. Right? This is something we proved a while ago. If you have a linearly independent set inside of Rm, you can always extend it to a basis. All right, now let's define, now that we have a nice basis for Rm, let's define a linear transformation S from Rm to Rn using these assignments. So let's say S of W1 is V1, and so on. S of W2 is V2, and all the way up to S of Wn is Vn. Well, remember, to define a linear transformation, I have to tell you what the linear transformation does to a basis. So here I've done part of a basis, but now I have to do the rest of it. Oh, there should be an n here. All right, so what happens to the next w? That would be w sub n plus 1. Let's send that to 0. And all of the rest of the w's up to w sub m, let's send those all to 0. Okay, now I've defined this linear transformation on a basis, and that means I've defined this linear transformation everywhere. So now all we need to do is let's check that S composed with T really is the identity on Rn. Okay, so let's take some vector v in Rn. We can write v as a linear combination of our basis vectors. So v is equal to a1 v1 plus dot 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 up to a n vn. So to compare these two linear transformations, what I'm going to do is just check that if we do S of t of v, what we're going to do is just check that this is the same thing as v, right? So there's going to be some big calculation that fills in the gap here. Well, S of t of v, v is this linear combination, right? So this is a1 v1 plus dot 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 down to a n vn. But then we can use the linear transformation property of t. This is a1 t of v1 plus dot 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 down to a n t of vn. But what is t of v1? Well, t of v1 is w1. That was what we called w1. And so on down to a sub n wn. But now we can use the linear transformation process or property for s. We get a1 s of w1 plus dot 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 down to a n s of wn. But what is s of w1? Well, s of w1 is just v1. So this is a1 v1 plus dot 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 down to a n vn. But that's v, so we did it, right? We're done. This linear transformation that I defined really is a left inverse for t. You can see the choices that I made here for how to complete the definition of S on these extended vectors that I had to write down to get a basis. I never actually used these values, so I could have chosen any vector for these instead of these zeros here, and it wouldn't have changed this calculation. All right, so at this point we know that if t is 1 to 1, then t has a left inverse. But to know that these are equivalent, we have to prove this the other way. We have to assume if t has a left inverse, then it's 1 to 1. So let's prove it. So suppose t, which remember is going from Rn to Rm, although this would work if we had any subspaces here instead of the whole Euclidean spaces. But anyway, suppose t from Rn to Rm has a left inverse, and let's call it S. So S is going from Rm to Rn, and S of t of any vector is just the same vector, right? This is what it means to be a left inverse. Okay, we need to show that t is 1 to 1. That's our goal. So how do you show something is 1 to 1? Well, you assume that t of v equals t of w, then show that v equals w, right? So let's see, what could we do? Well, we have this left inverse. Let's apply the left inverse to both sides. So now we have s of t of v equals s of t of w. But what is s of t of v? Well, look, s of t of v is v. And what's s of t of w? Well, by the same token, s of t of w is w. And so v has to equal w. And so we've shown what we needed to show. So t is indeed 1-to-1. It's kind of funny that showing that 1 implies 5 is hard, and showing that 5 implies 1 is actually super easy. So all of these properties are really equivalent to being 1-to-1. I think maybe the most the property here that sort of gives me the greatest geometric intuition for what a 1-to-1 transformation is this nullity one. Remember, nullity is a measure of how much a linear transformation, or how many dimensions a linear transformation squashes things down when you're moving from your domain space to your codomain space. But if the nullity is 0, that means that no dimensions get squashed down. And so you end up with, right, so just for example, from R2 to R3, I can't, R3, there we go. R2 looks like the plane. If we have a linear transformation that doesn't do any squashing, then when we somehow stick R2 into R3, but without squashing any dimensions down, that means we end up with a plane that looks just like R2, sitting in R3. It might be tipped. It does have to go through the origin, but it might be tipped in any orientation, but it still looks essentially like R2. And that's because we haven't squished down any dimensions, right? If we took, so this is 1-to-1, 1-to-1. If we have a transformation that isn't 1-to-1, well, it might squash down maybe the y-axis, so everything along the y-axis gets squashed down to 0, and that would just end up looking like a line sitting in 3 space, right?